Hello everyone. Hello everyone. A very good evening to you all. This is Pragya, your host for the Masterclass. It's so great to see you all here. Happy to welcome you all to today's Masterclass on leveraging data insights for decision making. Feel free to drop a hi or a hello or any comments for the speaker or me in the chat window. In the next 2.5 hours, we will look at typical journey of making data-driven decisions and overview of techniques and processes, making forecasts and simulations, and a lot more. Grab a cup of coffee, a notepad, and let's begin with today's session. Before we start today's insightful session, let me give you a quick intro to the Institute. The Institute of Product Leadership is Asia's first business school providing accredited degree programs and certification courses in product management, product leadership, data science, design, strategy, and leadership. The Institute has partnered with three universities in India and the University of Houston in the United States. The Institute was founded in 2012 with a singular mission of creating 10,000 plus product leaders in the country. Ever since, the organization has designed and delivered programs in collaboration with various institutes, universities, and corporates to senior working professionals to help them make career transition into product leadership. The Institute has built and developed a community of over 3,000 plus successful alumni leading to product, data, and design teams across the world. We are also knowledge partners for 240 plus organizations worldwide. You can find out more about the Institute and the programs offered on our website. Please check the chat window for the URL. And for those who have joined us via LinkedIn, please check the comment section for the URL. Folks, the post-graduation program in data science and business analytics is industry-recognized certification in data science and business analytics, which provides a data-driven viewpoint on strategic decision by applying business analytics and data analytics to real-world situations. Data science and business analytics courses are created and curated by industry CXOs with case studies, simulations, real-life projects, assignments, and personalized coaching. So go ahead and scan the QR code to know more about the program. Take a moment to scan the QR code. So once a speaker presents his insights, we will open up for questions. Please keep the questions ready. You can post your questions on Zoom Q&A window. This session is being streamed live on LinkedIn, YouTube, Facebook, and Twitter. So viewers on any of these channels, please feel free to post your questions in the comment section and we'll share it with the speaker. Here's some exciting news for all the attendees today. You have an opportunity to win Taylor Scholarship worth $200. The best asked question in today's session will get this reward. Please click the link in the chat window for details. So without further delay, allow me to welcome the very distinguished and eminent speaker of today's session, Saurav Chakrabarty. Saurav is the Director of Data Science at Freshworks. He leads the machine learning team of Freshservice. Freshservice is a cloud-based ITSM software for your service desk with a powerful automation tool to manage incidents, assets, and operations. He builds services that power our virtual agent and agent assistant features. He's also a faculty member at Institute of Product Leadership. Pleased to welcome you, Saurav. Handing over the session to you.
Thank you, Pragya. And hello, everyone. And Pragya, if you don't mind, can you just allow me to share my video?
Yeah, Saurav, one second.
Hey, thanks, Pragya, and hello, everyone. So, like Pragya, thank you for the introduction. My name is Saurabh Chakrabarty, as Pragya said, part of the data science team, machine learning engineering team at Freshworks. And in particular, I deal with the data science machine learning projects for one of the products in Freshworks, which is Freshservice. So, what I'll do in the session today is walk through some examples, some world famous examples of how data science has been used to solve certain problems. And I'll suffix each of those with uh, one experience from my personal life on projects that I have worked with. I'd strongly encourage you to uh, put your questions on the chat as soon as you have them, because we'll go through multiple topics, and it'll be easier to answer those questions right then and there than come back to all of those at a later point. So with that, let me get started on the session today. All right. So we're going to talk about data-driven decision making. Now, many of these terms that we use today in the industry have been used in various contexts in various different ways. So it's not very easy to sort of understand in what context I'm saying what. I'll try my best to therefore give you some examples, some case studies as we go along, so that you understand what I mean. And also remember that not everybody would use some of these terms in exactly the same way that I have been using. So there are, even in the industry, there is some differences in the way um, we do these, right? Before I'll just, quick introduction, a little bit more about myself. I'm an electrical engineer from IIT Kharagpur, an MBA from IIM Calcutta. I am more of an engineer than an MBA. My almost full time of my work is on the engineering side. My first introduction to statistics was in GE back in 2005, so many years ago, where GE was a pioneer in using data to drive decision making. They introduced the idea of Six Sigma, they introduced the idea of process control, they introduced the idea of reliability engineering. And these were some of the first sort of areas where data science, or what we today call as machine learning type sort of activities was done. Since then, I have seen this field evolve from statistics. Then we had this idea of big data. Then we had this idea of data science. Then we had this idea of machine learning. Then we have the idea of AI, deep learning. So we have these terms which are continuing, and I'll try my best to sort of give you a glimpse of how these things looked. I am presently at Freshworks, where like I said, I lead the engineering team. Yes. I think we have a question here, or somebody raised a hand. What do we do about this, Pragya? Should we allow them to talk and ask the question?
1 second. Shivansh, you can go ahead and ask your question. Shivanshu, sorry. Shivanshu, you can unmute yourself and ask the question. Okay, let's move forward
Okay,
then.
let's move on. It'll be good if you post the question on the chat. I think that's easier for us to review. So here is, like I said, today's agenda. I'll talk about some of the global, world famous examples of sorts. I'll talk about some success stories from my career. I'll also talk about some failures from my career. I think that is also critical for this. And then I'll talk about enablers. So what is the reason why some of these failed? Some of the things that I undertook failed, and what is the reason some of them did well? And try to make sense of what would make a successful data science project. All right. So this is a branch of data science which goes back many years, 20 years, probably even more probably. This is called reliability engineering. And this is a branch which deals with predicting failures of equipment. So when I was saying that in G back in 2002, I was introduced to statistics. These were some of the kinds of projects that we used to do. So as you know, G manufactures large turbines, equipment, aircraft engines, and so on, right? Um, you need to understand the reliability of these systems. And by reliability, I mean uh, so if you take a large engine, right, like an aircraft engine, it in turn consists of multiple smaller subcomponents. So what is the reliability of the overall system, given that each of the subcomponents have their own reliability? What some of that science over there predicted was that all of these kinds of equipments have a failure rate which looks like this chart, right? So on here you have time and you have the failure rates on this axis. So you'd see that over a period of time, there is the failure rate, the overall failure rate starts at a very high level. So there's a lot of failure initially, then sort of reduces, and then finally again increases. So these phases of failure rates are called like infant mortality, which is the hiccups when you start something, right? Like you for example, if you buy a new car, you will be asked to get the service done immediately, right? Like within the first few, I think 1,000 kilometers, 1,000 or 2,000 kilometers, you have to get the first service done. And the reason for doing that is some of these things require they fail early. They tend to fail. Uh, they tend to. Sorry, my mouse has disappeared. Hold on. Okay, so so this is so these are the first failures when this is called infant mortality. After that, you have random failures. So these don't have a very good reason for failing, but randomly something fails. After that, you have these wear out failures. So wear out failures are basically your equipment has been, this is like an old car, right? So that car has been running for a long time, and then it slowly starts giving you more problems over a period of time, and then it reaches its end of life, and then it just doesn't work anymore. Um, so these were the first these were things that one of the first few things that we as statisticians started to work on, to understand when things will fail. Now you realize that some of these things, right, they are because they are subcomponent level. So this is a subcomponent modeling. So the failure of a car is not the car, right? The failure of the car is also if the gearbox fails, if the engine fails, if the transmission fails, if the steering fails, if the brakes fail, all of them are failure. Now, the brake also will have a curve like this, but the difference between the brake and the difference between the brake failure and the um, and let's say the gearbox failure would be the time and the failure rates. So uh, gearbox might have much lower failure, whereas brakes might have a much higher failure, right? So based on these rates, the curve for gearbox might be high, so failure is higher, whereas the failure rate for brakes might be lower, so the failure is lower. And the overall failure is in some way the sum of these two failure rates, and not directly. There's a complicated way of getting to that. But the overall reliability is sort of the sum of all these failures. So these were some of the early sort of problems that we in data science tried to solve. Let me just quickly see if there is any questions here. I don't see anything, so let's move on. Now, if you think about these kinds of problems, right? Let me share a very famous example. This is from this paper by NASA, and this is how NASA measures the reliability of their spacecrafts. So the s- the space station, etc., which are orbiting Earth at this point of time. This is how they do it. Here, I would like to introduce a little more technical sort of topic, right? So if you look at this curve here, right, this red curve gives you the operating conditions. It says uh, that the stress on the system has various degrees. These kinds of curves are called distributions. So it has various, it looks like a pattern, right? There's a pattern to it. Multiple times, like what is the stress at time equal to 1 second, time equal to 2 second, time equal to 3 seconds. So you'd measure all of these stresses and you'd compute a curve like this bell-shaped curve. And you would also compute your material strength. So the material strength also will vary depending on the quality of the material, the exactly even small differences in the material will change the material strength to some extent. So your material strength should be higher than your stress. So if you look at if you imagine this axis as the overall stress, right? So the strength of the material is higher than the stress. So the green curve is on the right side is more stronger, and this red curve is on the left side, which means it is not so strong. But in this area, you have uh, stress. You have an intersection of these two things. So if the operating stress goes beyond certain level, this level, it goes beyond this red line, and the material strength is lower than this line, then you immediately have a failure, right? So this is how NASA would compute its reliability index. They would try to think of possible scenarios where the stress will be high, like here in this place. In this place, there will be higher stress, whereas the material will be poor in this space. And because the stress is now higher than the material strength, your equipment will fail. In any other condition, if your strength is high, but material strength is higher, this part, then your equipment doesn't fail. If your material strength is low, but operating strength is even lower, this side, then again your material doesn't fail. So this is one way in which you would compute reliability of equipment and use it to decide uh, whether to go forward with the particular design or not, right? Any questions from anyone so far? Okay. So this is one example. This is a very traditional data science approach where you would measure statistical properties about operating stress. So you'd measure operating stress over a period of time, compute some statistical properties about the operating stress. You would take different kinds of materials and again compute the statistical properties of that material and use these two to identify what material is good for what operating condition and what would be the probability of failure if stress is higher than the strength. Similarly, when NASA wants to measure the reliability, the operating reliability, so this is design reliability, and then there is, so design reliability is how well are we designing our system, right? And operating reliability is design reliability is one part of it, but there is also process reliability. So you tend to see that, have we maintained the process in the right way? Is our manufacturing process correct? Is our launch process correct? Is our assembly process correct? Have we put all the components together in the right way? And you'd use data there to identify if your process and in your design are in right place. And then you would, for this overall system, you would come up with a number and say the probability of this failing, this aircraft, this space shuttle exploding or breaking down or something bad happening, is 1 in a billion, or is so it is like 1 in a billion chance that something bad will happen. So that is how this field of reliability analytics works. The next type of analysis that, again, this is a very traditional approach, and this is a very well-known examples exist in this space. Both this example and my previous example are based on data which has been collected over a period of time through process, through measurements in the manufacturing systems, and then we are trying to make sense of it. So it's historical data which has been collected. So market basket analysis is basically the idea is pattern mining. So let's take an example to understand what we do here, right? For a market basket analysis, think of this, right? Think of, let's say you are given a bunch of invoices. So you go to a shopping market, you buy certain things, you go to the checkout counter, and they give you a bill, an invoice for all of this, right? Market basket analysis deals with identifying the patterns which are present in these bills. So each individual sort of invoice is one data point for you. And what you would try to determine using machine learning, data science, or whatever techniques you can, is something which is shown on the right side. So I'll take a few minutes to explain what this right side is. So let's say you had 1 million customers who had come in last year, and each of them had bought some combination of things from your store. So each of that invoice, let's say this is the invoice, each of this invoice has item number 1, item number 2, item number 3, and so on, right? One is this customer A. Similarly, you would have customer B. Customer B also would have item number something, something, something. Some of these items might be common, some of them might be not be common. So the number of customers that you have is 1 million, and maybe the number of items that you have in stock is 10,000 items. So these items could be one of the 10,000 items that you store, that you have in your shop. And there are 1 million unique customers who had come into your store, and each of them had bought something from your store, right? So after looking at all of these bills, all of these invoices, you would see that what are the items that are bought together. So each of these circle is one of those unique items that you store in your shop. So for example, you store ketchup, you store eggs, you store sausages, you store cereals, you store milk, and so on. And what this graphical representation shows you is that, for example, whenever people buy cereals, they also buy these kinds of things together with that, right? So cereal is connected to all of these things. So people who buy cereal typically also buy milk and muesli and yogurt. So they are all close by. They're all close by. So these are things which are. But people who buy cereals are very less likely to buy salt, pepper together. So there is no connection between them, which means that somebody who has bought yogurt is not buying pepper on the same day, right? But somebody who's buying muesli is probably also buying tofu or buying mushrooms. So this is how the graphical representation of market basket analysis looks like, right? Representation of a market basket analysis looks like. And once you have this kind of analysis done, you will use it in various kinds of things. So what you will do it is you will use it for product placement. So if people are buying milk and yogurt together, depending on your strategy, you might kind of keep them in the nearby places. If, for example, people are buying salt and pepper together, then you would again want to keep them in nearby places, or you might even want to keep them distant so that people actually travel in different parts of your store. Similarly, you can do the physical shelf arrangement. That is, see, this is white bread here, this is brown bread here. You might want to keep both of them in the similar place because people buy in those things in cohort. You could also do this upsell, cross-sell, and bundling. So upsell means you somebody who has come in to buy cereals, you try to convert them to muesli, which is probably a little higher in price. So you upsell them, right? Or you cross-sell them. Like somebody who buys cereal, you try to sell them milk. And finally, you also use it for customer retention. And what I mean by that is when you realize that somebody is about to leave, you give them offers. You tell them that, hey, I saw that you have bought tofu. Here is some good quality mushrooms that you might enjoy. So that way you retain your customers. So this is how the market basket analysis works. This is again, these kinds of areas, the previous example in this areas traditionally has been known as data mining. And why is it called data mining? Because all of this data is sort of hidden in a mine somewhere, and you go and fish out, you go and find out all of these nuggets of information and use it. So historically, these have been known as data mining. And a variant of this approach today is used for movie recommendations. So, so imagine that me as a person is watching two movies together. Like I watch one movie after the other. So you can go to a new person and say, when people watch this movie, they also watch the other movie. So why don't you go and try that? So when you see Netflix or Amazon Prime showing you those snippets. Like these snippets, right? When you go to Netflix, you get this, and they'll show you some. For example, in crimes and thrillers, they'll show you these examples. So, how do they get these examples? They get these examples from this kind of. It's not exactly market basket, but some variant of that is used here. I'm sorry. So Lokesh is saying keywords matter. Example, horror thriller. Keywords when you are searching for movies, yes. When you're searching for movies, then yes, keywords matter. But I don't know if that is the question. But my point is that even if you don't, if you go and if you go to your Netflix screen and put this there, you will see a completely different list. And you'll get a different list because that list is customized to your example. So this isn't a search per se. This is recommendation. Is there any kind of algorithm that Netflix uses? Of course, this is there is an algorithm which Netflix uses. It is called a recommendation engine. The algorithm for that is unfortunately, I think, secret from Netflix's end. But there is a um, but it is similar to what I showed you. It is the approach is similar. They add some more items like your demography, location, um, and so on. But basically, it's the same approach. If they are able to figure out that you and I, like for example, Aditya, you and I are of the same sort of nature, and I have watched these three movies, and you have watched only two of them, then they will recommend the third movie which I have watched to you, because that would make the recommendation more real. So that is how they do this. Okay, Lokesh, I hope I answered your question. If not, just let me know. Previous watched movies related recommendation. I'll just Lokesh, would you mind just I'll unmute you. Can you just call out what you are saying so that it's easier for us to understand? Lokesh, I've given you. You can say your question out if you want to. Okay. Yeah, his mic is not working. You are right. The previously watched movies, etc., is how they start building the profile for you. And once so there is an algorithm that there's some more nuances than what we can cover here. But it's the reason for bringing this up is it is similar to this. It is similar to the idea that if you are watching this movie, think of this as movie, and you have watched related movies, right? All these close by movies, then you would be recommended movies from this region. So anyone who comes in would be recommended movies from this region, and you will not be recommended movies here because this isn't a movie that these kinds of people want to watch. All right. Now, okay. Now, this again a world famous example of Target. This goes back quite some years. I don't know if you know this example, but it's a very cool example. So I added it to this. So Target, the retail shop Target was one of the first companies to adopt a whole bunch of these data science, data mining techniques, right? So there was this guy called Andrew Pohl, and he did this whole bunch of analysis to figure out, right, what are people watching, what are people not watching, and he started creating these programs in which, based on the propensity of what you would buy, uh, Target would send you coupons. So let's say you are uh, mm, you are purchasing a lot of bread, right? Let's say they would send you a coupon um, for cheese, because they know that this guy is a bread eater. Maybe he'll like cheese, and so on. So something like that. Now, what happened is there's an actual example that they noticed that that women were buying larger quantities of unscented lotion around their when they were pregnant, and they were buying supplements like calcium, magnesium, zinc, etc., etc. Right? So they did this analysis, and basically there's a nice article. I'll try and send this article to you on chat so that you all can read it also. Um, they send out coupons to to somebody who they thought was pregnant, and that person's father got those coupons. She was a young girl. He got those coupons, and he came back to Target, and he sort of shouted at the manager, saying that, "How dare you send these coupons to my daughter? These are all coupons for maternity products. Why are you sending them?" So the manager sort of apologized and said, "Okay, sorry, we made a mistake. Happens," and he let it go. After a few days, he called that person back and said, "Okay, hey, I know that we made a mistake. It is, I'm just calling you to say we are sorry once again." And then the father says, "Okay, I should say sorry because she is actually, we didn't know, but she's actually pregnant and something has happened." So it was, this is both a famous example and infamous example. Famous because this is a very good use case of data science in action, but it also shows a little bit of intrusiveness, right? Like, um, these guys sitting in the back end doing all this analysis know a lot more about you than what you want to uh, sort of show. So people didn't. Some people didn't take it in the way you would sort of expect. I'm posting this link on the chat. Just whenever you guys have time, just have a look at this. Right. Today, these approaches are extremely common. You every time you watch a movie, you go and buy something on Myntra. Any of these cases, any time you touch any of these things, you are part of this sort of experiment. Whether you know it or not, you are part of that. And then this kind of logic is used in other places as well, Twitter, Facebook, etc., to understand who you are as a person and send things to you uh, which everybody uh, sort of everybody yeah, at this point of time these examples were rarer. This example is 10 years ago, but this is rarer. So today it's fairly common. Everywhere you go, you are bombarded with this kind of analysis. All right. The next example, this is from my personal experience. This is a project which I did about 10 years ago. It was not a successful project. So, and I'll sort of tell you what went wrong and what was this about. So in this project, we were trying to predict. So now you have a little understanding of the data science involved, right? You know that you can mine for these events, like things happening together, frequency, how frequent are two things occurring together, and those kinds of things. You also understand that there is some amount of, you can use math and stat to sort of predict reliability of things. And as part of my project, we decided to merge these two to predict failure of telecom equipment, right? So if you see our large mobile towers, you would see that they have those big antennas and all, right? And they have other network switches, other equipment which allow them to transmit data and phone call to your phone. We wanted to predict the failure of this. What happens in this case is, what happens in this case is there is a whole amount of data which is coming back to the central server. Like it would say restart, something started, some update happened, so you see that this is how this some login happened, some logout happened, and so on, right? So this is that is basically a computer which is running all your network stuff for you. So, and that computer does all these kinds of things, right? Now, what you can do is basically you can extract these keywords from these logs, right? So you could use Python scripts and so on to extract some of these uh, things. And you can see when something fails, right? So your end goal is to find failure. So you're trying to predict failure, right? So you would go failure minus 5 stages. So this is failure minus first stage, failure minus second stage, failure minus third stage, fourth and fifth. So server failed. What happened before server failed? You got access denied. And what happened before access denied? You got again an access denied. You got connection refused. You got connection refused. So there were a bunch of things which happened before you got server failure. And you see that this last one is also server failure. But this server failure happened in a different way. So here it was access denied, here it was request failed, here it was request failed, here it was connection refused, here it was connection refused, and request failed. So, some differences in the way, it's not necessary that all failures are always happening the same way, right? So different ways, different things happen. But if you're able to extract all this information using the sort of previous examples, and you have enough instances of things failing, then using your previous examples, you can do this pattern mining. You could mine for events which would lead to failure. And why would you want to do that? You basically, before the server fails here, in stage one itself, you want to let everybody know that, hey, your server is going to fail. That way, they can take some action. They can do something to prevent the server from failure or prevent this firewall from failure. So this was the goal, so this server failure, we would do a pattern mapping, and this pattern matching would give us. So it is also got sequence matching because it's a little different because here there is a sequence. So stage 1, stage 2, stage 3, and so on. So if you look at the server failure, right? Before server failure, these are the frequent events which happen. And ignore some of the technical parts. It's fine. We don't need to worry about it. But using these patterns for firewall failure, using the patterns for router failure, even at stage 1, you can start creating prediction of when something will fail. Right. So you can say that, oh, I got two connection refused errors, which means the probability of server failure is high. So this is the goal, and this was reasonably successful. The way we could predict failures in a reasonable way, right? But it did not work out well practically. So it did not work out well practically because there is a huge technical challenge. So if you look at this, right, you'd see that these things are coming at the same time. So you see this 010009, all 4 events have happened at the same time. So they're like microsecond kind of difference between something's happening. So you need to have a very strong system which can process such high-speed events. It's not very easy to process these kinds of events. And we are talking about 10 years ago, where some of these technologies were even more nascent, and we couldn't even scale that. So this prediction becomes useful only if stage 1 happens 1 day before failure, right? So that I can tell you, this server is going to fail, and then you can send somebody over to that network, do something, right? But if this is happening in a few milliseconds, then the whole thing is pointless, right? Even if it isn't, right? Even if it isn't a few milliseconds, it's actually a few, it gives you some sort of warning. Still, processing this at this high speed is a challenge. And you are talking about millions of possibly different types of events which are coming in. So that was the technology challenge. The next problem in this case was the cost of false positive. Now, this is an interesting one. False positive basically means that you predicted a failure, but it did not actually fail. And what would you like? What happens when you predict failure? When you predict failure, somebody runs, goes there, does a check, maybe even replaces the part, and then comes back. Now this is expensive. Somebody going, doing something, replacing a part, all of this is expensive. But it was never meant to fail. Right? It is perfectly fine. The error was just a random. So you like when you're doing this mining, you would realize that there is this notion of support and confidence. That is how confident you are that it will fail, and then uh, you are not very confident till the last stage, till fifth stage, that whether this will fail. With each successive time period, your confidence sort of increases. So there is a huge cost of this false positives, right? You send a person to go and repair, and then nothing has failed, so that person comes back, and that cost is probably higher than the cost of failure, and that is a challenge. The final issue is ROI. ROI is, let's say you are to build this complicated system which does this real-time processing, does all of this, and so on. Is that cheaper, or is keeping one redundant server cheaper, right? Or a redundant firewall cheaper? And in many cases, you will we realize that actually keeping, instead of doing all of this, you just keep one extra server there so that if one fails, the other takes over. So you have a backup, and that backup is cheaper than doing all of this. So this project failed, in spite of the fact that we are pretty good in predicting failures and things like that. The ROI simply did not exist. And in data science projects, unfortunately, you will find some of these cases, because till you have done all of this analysis, you wouldn't know what is the actual your accuracy levels, right? You wouldn't know how many false positives are you going to make. False positives, by the way, means that you are predicting something, but that doesn't happen. So it's a false positive. And that, sort of creates a little bit of an issue in data science projects. So all the effort that you would put in would go waste, because after doing all this, you'll realize that the model is not accurate enough for us to take it to a full scale development. Right? Okay. That brings us to end of this session, this part of the presentation, where we spoke about some of the older historical approaches to do data science. So these are all pattern matching, market basket analysis, and those kinds of what am I doing? Those kinds of things which are little older, in their. I don't want to use the older, newer technology, but these have been existing for a long time. People have been using these techniques since the 90s, early 2000s also, right? So that is these are those sort of techniques, but they are very relevant for today's world. Everybody is still using it. All tech companies have some version of this. In fresh service, we are trying to predict failure of equipments, not using exactly similar technique, but something which will be similar, where we also are trying to predict failure of cloud-based equipment. So although these ideas have been around for a while, the actual implementations are still going on. All right. So I'll pause a minute for any questions if you have, and then I'll move on to the next section. Okay. Moving on. The next part, again, these are ideas which have been developing since a long time. Till this point of time, we spoke about things where you have data. So you had some data with you, and you were mining for that data. You were doing a data mining activity. But what if you don't have the data, but you have an idea, right? For example, um, you know that something might work, but uh, you can't prove it. So that is called that's called an experiment. So what you do is you create a hypothesis. A hypothesis is basically a statement which says X is true, right? Then you set up an experiment, you run the experiment, collect, analyze data, and then you accept or reject the hypothesis. So your hypothesis was X is true. Now you either say, hey, yeah, yes, I have evidence to say that X is true, or you say that based on data, I don't have evidence to say X is true, so X must be false. In the abstract, this is what the idea of experiments is, but let me give you some concrete examples so that you understand it a little more clearly. So again, in the theme of some world famous examples before we go into my personal journey. So this is our clinical trial for COVID vaccines, which happened just last year, like a few days ago, right? The clinical trial is basically when you are trying to, you have the idea, like I said, you have an idea that you know the vaccine for um, COVID, right? You have the idea. So this is an experiment from Moderna, I think, Moderna or Pfizer, one of the first vaccines which came out. So you have the idea. You say that I believe this is the right vaccine for COVID, but you don't have the proof. So what you do is you run a experiment. So this is called a randomized controlled trial, RCT. And the way this trial is run is like this. So for this particular case, this is from their website. So it's true value. This is the phase 3. So they do it in different phases. Don't worry about it. But the clinical trial is basically you have 46,331 participants and at 153 sites. So you recruit so many people, 46,000 people, to come and take the medicine from you, right? And these are spread at 153 different places. And these are, these are some of the geographies. So you see USA there, you see Brazil there, you see, I don't know, that's Argentina probably, you see South Africa. I don't know what these countries are. Maybe it's Turkey or Iran. And then somewhere in Europe, there is one more country. So these are the country. Oh, okay, they have written it. Correct. This is Turkey, South Africa, and Germany. So these are the countries where you go and you pick up your people. These are the type of people. You have Asians 5%, Blacks 10%, Hispanics 26%, Native American 1%. 49% are male, 50% are female. Participants 12 to 15 are 2000, 16, 17, so many. Okay, right. So this is how your trial is. You have created your participant group. Now, what you do in this randomized controlled trial kind of thing is you give half of your patients the vaccine, and the other half of your patient, you basically give them a dummy. It's called a placebo. So you don't give them the actual vaccine. You give them whatever, salt water or something like that. You inject them with that. And by doing that, you create this randomization process. So what happens then is you don't tell who gets what. So all your sort of participants think that they got the vaccine or they didn't get the vaccine. They don't have any way of knowing whether they got the vaccine or not. And you tell them, you go about your life in your normal way, and you observe them to see if they develop any COVID symptoms, they get COVID or not. And using this data, you prove whether COVID vaccines are effective or not. If the COVID vaccines were effective, people who got the vaccine would not get COVID, or would have lesser COVID, lesser chances of getting COVID. Whereas people who did not get COVID vaccines, got the placebo, the salt water, they would they would have more COVID cases in their case. So this is the kind of trial that you would do to sort of prove, um, not prove, but conclude whether COVID vaccines are effective or not. Any questions on this? Anyone? Okay. And just to give you a little more of details here, you would basically create two groups, a group A and a group B, and you would measure. So this group A gets the medicine, group A doesn't get the medicine. You would measure whether somebody gets COVID. So if the person one gets COVID, you mark it as plus. Doesn't get COVID, you mark it as minus. Group B, similarly, you do plus minus and so on. Finally, you compute the average. You say in group A, people who took the medicine, 40% got COVID. In group B, people who did not take the vaccine, 80% got COVID. And using this, if you remember early phases of the COVID, they will say Moderna vaccine is 90% effective. Right? So they would then compute the statistical figure and say that what is the effectiveness of this is dashboard, right? To show data graphics format. What is the dashboard? I'm sorry, Lokesh, I didn't get that. Okay, so Lokesh, I'll come back to this question once. Using these two, sort of placebo and non-placebo groups, you would compute and tell them that my vaccine is 80, 90, 70, whatever percent effective. Okay, sorry, Lokesh, can you just call out the question? Your mic is still not working, right? So I didn't quite understand your question. Which dashboard are you talking about? All right, I'll move on. Okay, so what are some other examples of this, right? This randomized control trial is also, in some senses, called the A/B test, and this is used very frequently for website design. So here is an example. This is Humana. Humana is an insurance company. So this was their original website, right? This was their original website. This one. This was the original website, and this looked like this. And they had, some measure of success. They wanted people to take their buy whatever they have, like this particular thing. And so this is the control. This is as is control group, and this is the treatment group. So what you do is you create one design of website. This is design 1, and you create another website of the design, which is design 2. And whenever people come to your website, randomly, you send some of those people to this version, and you keep the rest of the people to this version. And you measure. So here you see this call to action, right? Shop for plans. And here you have this call to action, get started now. And you see how, in which websites are people clicking on this call to action more frequently, right? So you send people to this group, And again, in the similar way, you will create a table for group A, this website, and group B, this website. And using so in group X, you do the same thing. This is person one coming to, did he click or not? If he clicks, then it is one. Person two did not click, so zero. Person three clicked, so one, so on. And similarly, in group B, person one clicked, then it is one. And then at the end, you just compute the average of these two groups and then try to say that which of these groups are, which of these websites are more effective. So essentially, in this example, they redesigned the website to this, and that allowed them to get more customers for their product. So that's an example of A/B test. Again, every time you're using any website, this is a very, very, very frequent approach to do it. All companies roll out any of their UI changes, any of their functionality changes using this approach, using a A/B test kind of approach. Okay. Any questions on this? Anybody other than Lokesh? I'm just going to dismiss Lokesh's question because I didn't understand it. Now let's talk about my experiments. Some work which I did in this space where I had to use control triads or A/B test. So I was working in a space which is called visual search and recommendation, right? This technique uses computer vision, that is image based techniques, to create recommendations for websites. So let me give you these two examples. This Zillow is a website by Zillow is a real estate website in US where you can go to buy rent cars, right? Sorry, what am I saying? Buy rent houses. Now, what we wanted to do as part of our project. So you'd see this house. This house has a particular look, like whatever this brick, looks like a hut and so on. Like what, I don't know what is the name of this kind of look, but you have this look. It also has certain properties. So the properties you typically have house properties, like I don't see the thing here, but you would have house properties like this, right? 3-bedroom, 1700 square foot, 3 BA, I don't know what it means, but 5 is 5-bedroom, 3 bath, I think. 3 bath, 5-bedroom, 3 bath, and this is the house, and so on, right? So, and if I were to tell you that, find similar houses, you'd find similar for 5 bed, 3 bath, 1700 square foot kind of things, right? But what if that is not the goal? What if you wanted houses which have a similar look, like which are architecturally similar or something like that? So we designed a system in which you take this image of this. The inverter is making that continuous noise. Guys, can I take a 5-minute break? There is some power issue at my home. I'll just go check it out.
Yeah, sure. We can get back at 8:10.
Yeah, just give me 5 minutes. Let me go check out what is happening there.
Yeah, sure.
Hey, I'm back.
Hi, Saurav. Okay.
Hey, we can get started if
Yeah.
everybody is okay. So where I was saying that okay. So the project that we did. Okay, hold on. I'm losing my mouse. Just 1 second again. Yeah. So we were looking at visually similar homes. So we won't compare just the beds and bath and square foot and all, but houses which are look similar. So this house and this house look similar. This and this look similar. This and this look similar. And based on the similarity of the looks, we will try to predict. We'll try to give you recommendations. So obviously, I mean, we created a system. There's a lot of machine learning in the background, which is happening, but that's not the point here. The point is, how do we know that people are actually buying more houses if they see similar houses, right? Like what makes this look a better way to talk about houses than say this bed and bathroom kind of thing. So to do that, Zillow was not the company I was working with. I was working with a different company. They're called Realtor.com. But to do this, what you would do is you would create such predictions of similar looking houses, and you would predict, you would give these recommendations here, only to some percentage of your customers, a small percentage. Why a small percentage? Because you already have a system live in prediction, live with the system, right? Where you are giving predictions based on these properties. Now you don't want to immediately change it, because if this system is actually very bad, then all of your customers will be impacted. So maybe to 1 or 2% of your customers, you would show this. And then you would measure the change in the conversion rates. If these conversion rates after showing visual recommendation is higher, then you would start showing more visual recommendations. And if it is not, then you'll show lower. We did a similar project called Style Scanner for Apple, a very similar idea. But again, if you look at this dress, right, this particular dress, you could, of course, so if you look at, this is, I think, from one of the Indian websites, Jabong or Myntra, or one of them. So here you see how they define this shirt. They'll say men, black, solid, top, SS, yoga, dry fit, slim, fit, round neck, training. So these are the tags, these are the properties which are used to describe this. So the equivalent of 5 bed and 3 bath in the house space suddenly becomes so many things, right? So when somebody says, I want a t-shirt similar to this t-shirt, they actually are looking for similarity along one of these things. So they might want a yoga t-shirt, so that is what the similarity is. Or they might want a black t-shirt, so that is what the similarity is. Or they might want a round neck t-shirt, so that is where the similarity is. So you can't actually, similarity is a vaguely defined notion. So we again used a similarity based on visual similarity. So you use machine learning to find out similarity scores between different dresses and then predict one. So for example, in this particular case, you have similar products, which are these, right? This is similar because the neck is probably the same. This is similar because the color is the same. This is similar, again, probably because of the neck or yoga or whatever, one of those things are the same, and so on. So using this, you create similarity scores. And this was one of the other projects that I was working on. And in both the cases, the relationship to the A/B testing remains the same. You want you want to measure whether this visual similarity gives you a higher conversion or not. If it does, then you would show more of them. If it doesn't, then you will not show any of them. So that's how this works. And all of this is done in that framework that I described earlier, right? Uh, that you do A/B testing. You show one design of the website to some people, the second design to some other people, and then use the differences to see how it works. All right. So this is my personal take on these kinds of projects where you use data to take some sort of decisions. Next, we'll talk about AI. And again, I'll pause here for a minute if you have any questions. All right, then moving on. Surprisingly, the field of AI is actually pretty old. Although in popular term here, you feel that AI is the latest thing. It actually isn't. The foundation of the work was started in 1940s by this guy. Anyone knows what is the name of this guy? You can type into the chat if you know. No one? This guy is Alan Turing. He was a British mathematician, and he worked in World War II in the Enigma project. That is, he tried to break the German secret code, and he laid the foundation of this AI. In fact, today, if you want to say that, when do we say that something is artificially intelligent? We use a test known as Turing's test to sort of do that. But anyway, that's history. 1940s, he laid the foundational work of AI. In 1952, the first conference was held on AI. But what happened is, initially there was a lot of, we will solve it. So for example, this guy, Marvin Minsky, this Marvin Minsky. Marvin Minsky says, within a generation, the problem of creating artificial intelligence. So there's a lot of hype there, and that hype did not pan out. And the hype did not pan out in the industry. This is known as the AI winter. There was an AI winter which came in, and techniques which had been invented till that point of time was junk. We could not see results, and so on. This continued till about the 80s. In the 80s, some new techniques came in, and again there was a lot of hope, a lot of hype. Expert systems were designed. Neural networks came back. Back propagation, a technique of working with neural networks, was invented. This again went for some time, but again it didn't pan out that well. Very quickly, people realized that isn't sufficient, and this idea of expert systems was kind of again junked. So there was again winter. So when I say winter, it means funding is low, excitement is low in this area. In 1993 is when we see again resurgence of all of this again. Do you guys know what is happening here? Can somebody tell me what is happening in this image here? Anyone wants to guess? Yeah, the computer defeated a grandmaster of chess. That's very close. Who's the grandmaster who gets defeated? Correct. So this is Kasparov getting beaten, and Kasparov was the reigning world champion. He just wasn't the grandmaster; he was also the world champion at that point of time. Gary Kasparov is getting beaten by the computer program developed by IBM called Deep Blue. And this is Gary Kasparov sort of struggling with the idea that a computer is beaten him. Till that point of time, nobody believed computer would ever be able to do that. Right? And so that kind of kindled a lot of hype. Wow, computers are beating human beings in chess, and that was fantastic. After that, this as I said was suddenly people were super excited about it. In 2000s, there is a new sort of technique in machine learning which was invented. This was called random forest. Till this point of time, you remember the approaches that I showed you: randomized control trial, then pattern mining, event sequence mining. All of these used standard statistical techniques, right? These are mathematical techniques which are known. Here, for the first time, we have a technique which is called black box algorithm. So nobody knows. I wouldn't say nobody knows. It's a hype to say nobody knows how it works. But basically, black box means you know less about it. Mathematically, the thing is not very clear why it works, but it works, right? It also has a the explainability is difficult, right? In the previous case, if somebody like goes back and says, why are you telling my system will fail? In the previous examples which I showed you, right? Or we go to NASA and say, why are you like only 10% confident of failure? NASA would say, oh, because component A has X%, component B has Y%, and if you add these together, you have mathematical statistical way of doing it. Here you don't have those kinds of things. You are learning from data, and how you are learning it is a little black boxy. So that is where this era starts. There was a huge fight at that point of time between these new approaches and the old statistical guys, and they sort of did not believe that this will ever work. But it did. In 2006, you may not know the names of all of these guys, but these are the pioneers of machine learning as it is known today. In 2006, they invented an area called deep neural network. Right? This is a special type of neural network which is very complicated, very sophisticated. They use GPUs. So till that point of time, deep neural network wasn't very easy to use because it required a computation power which nobody almost had, right? It is many times the computation power which is required by the chess engine here. So these GPUs came into picture, and they helped in working with this neural network. They are very powerful machines. This technique of back propagation was fine-tuned. The idea of activation layer was it. So let's not go into these technical details, but in 2006 till date, right? This is the predominant way of doing machine learning. And this has sort of revolutionized almost every field. So if you look from the progress today, right? In 93, Deep Blue defeated Kasparov. Today, chess is a solved problem. Like there is no human which can, there are computer programs which are based on this deep neural network kind of thing, which learns by itself and is impossible to beat. Another game called Go. This is also, this was also believed that humans would always be superior, but world champion was defeated by a chess program. All of these programs came in from Google's company called DeepMind. Lip reading. In many cases, you'd want specifically for people who can't hear properly, they lip read, or somebody lip reads for them. So there is experts in lip reading, and this has been solved by neural networks. So neural networks can lip read much better than any human being ever. They can transcribe better than most human beings. They can do multiple types of disease diagnosis much better than human doctors. Fractures, read X-rays, find out problems with neurons, with eyes. All of these are done much better with machine learning than any doctor can, right? Poker, news reporting. Believe it or not, today most of the news that you read are right. They are syndicated news. So what happens is there is one article which was published by company newspaper A, another article by newspaper B, a third article by newspaper C, and you use AI to sort of take like a few lines from here, few lines from here, few lines from here, merge them together and create a brand new news article for newspaper D. And this is very, very common, very, very frequently used, and it works very well. So let's say, things like, just imagine a situation like a company declares its report here. So you would have the news that company declares its annual results here. There is another small piece of news which says company A's share went up or went down, something like that. There will be another piece of news which says the CEO of the company made some statement. Now this D would create a full report which says, full news article which says CEO declared the result and CEO also made the statement. While based on this statement, the share price went up by 10%. All of this will basically be found by this example. And today, many newspapers are actually, using techniques like this. So this is the state of AI today. And probably as we, in our lifetime, we will see machines doing many, many, many things that humans are supposed to do better. We will see that that idea crumbling. Machines will start doing many of these things in a much better way. Have heard that lip reading is being used by some countries for spying and intelligence. That could possibly be true. But you had expert lip readers earlier also, right? You'd had multiple reasons to lip read, right? And you had experts there. Whether that expert was used to help somebody who couldn't hear or it was used for spying, I don't know that. But whatever be the case, a camera fitted with an AI system would lip read much better. Now you can put it for spy use or you can put it for good use. That is up to you. But the lip reading quality will be much better by computers. Okay. Any other question? Anyone else? All right. Let's move on. So, how are AI systems built? How much time do we have? Do we have 30 more minutes now?
Yes, we have 30 minutes to go.
30 minutes is my time, or do you need something from them?
5 minutes.
Okay. All right. So I'll just briefly go through it. Like, how do these things work? Let's take that example of chess that we were talking about, right? So this is how AI system works. You have an environment. This environment consists of This environment consists of whatever you see externally, right? Like if you are playing chess, then the environment is chessboard, your opponent, whatever else is important. It is only those things important. So if you're playing chess, probably the weather is not that important. So weather is not part of the environment. But if you are a self-driving car, then the environment, weather is also part of the environment, because for self-driving car environment, the weather is an important part, right? Then you have the process of perception. Perception is seeing or hearing or looking or feeling or knowing. So how do you know the state of the environment is the idea. So if you are a chess program, all you need to know is where are which pieces located, no, nothing else, right? If you're a self-driving car, you would need a camera to see the road in front. You would need a radar to to understand proximity. You need a lidar to do ranging. You need a speedometer to understand how fast you are going. You need an accelerometer to understand how you'd have this whole bunch of things which you would need if you were a self-driving car. So these sensors basically help you percept. Based on this inputs, what you perceive based on the sensors, you have an agent which learns, which knows, which figures out things, right? And the agent can take action. So the agents has some sort of hands and legs, using which they can take action, and that action will impact the environment. So this is how things happen. So if you had a self-driving car, you would have accelerator, and you would have brake, and you would have steering, and you would have a bunch of other things which you could push and pull and do something, and that would allow you to change your environment, and that environment is basically the car and the road and the system. So that is how a system like this would work, right? There are certain things which are baked into this, and that is rational agent and so on. But you get the idea. I'm not talking about. Let's not go too much into it. We'll otherwise run out of time. So this is how a system like this learns, and using that learning, it becomes intelligent. It does intelligent stuff. Let's move on here. The environment in which you are can change based on what you are trying to do, right? So, for example, if you are poker, then okay, let me first explain these things to you. So the environment could be fully observable. Fully observable means I can see everything which is there to see, right? For example, chess, everything you can see. You can see all the pieces on the board, everything is visible. But in poker, you don't have everything visible because there are certain cards which are not, you can't see your opponent's card. So that's partially observable. You could have deterministic versus stochastic system. Deterministic means you know what is going to happen. Stochastic means there's a random chance of something happening, something else happening. Again, if you think of poker, right, then you could have the dealer could give you a brand new card which you didn't know about. You could have discrete or continuous. Discrete means things change one at a time. Continuous means everything is changing. You could have benign versus adversarial. Benign means the environment is not fighting back with you. Adversarial means the environment is fighting back with you. So, for example, in chess, your opponent is trying to beat you. So whatever you do, your opponent is trying to sort of beat you. If you are in benign system, would be something like driving. The road is not trying to hit you back. So you have a benign system. So this is some properties of the environment, and based on this kinds of systems, you learn. This is the intuition of machine learning. And how do you learn? You learn, the base idea is very simple. You have a variable y, which you want to learn. That variable y is some function which is of all the inputs. So, think of, you want to learn what is the wage, what is going to be your salary today, given your age, your education, your number of years of experience, blah, 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 blah. And if you can create a formula like this, then you can probably go and negotiate with your employer and say that, according to this formula, I should get X. You're not giving me X, please increase my salary. And there is some correlation, like everybody, if you are working today, you know that using these kinds of things, you can at least figure out, if you are whatever, some sort of education, you get more. If you're that kind of job role, then you get more. If you're changing companies, you get more. So there are certain things which allow you to do it, and you can create a formula. You can learn a formula, not create. You can learn a formula like this. So this is how, and our goal is to learn this formula. So this is how sort of machine learning system works. Let me show you an actual example of machine learning systems in action. So what you do in a like if we are still talking about the same thing, like years of education, income. So what you do is you guess this curve. You guess this blue curve, right? Yes, sorry, you guess this blue curve. So this is your data. This on the right, on the left side, you have plotted the data. So you have one person who has 10 years of experience, as his or her income is here. You have another person who has 18 years of experience and his or her income is here, and so on, right? So you have this. Based on this, you guess. You say that, my guess is this blue line. This is what I think the formula for income is, right? Now this blue line, of course, doesn't go through all the red points, right? There is always a delta. See, for example, the blue line is here, the red line is here. So that is this is the delta. Here, the red line is here, the blue dot point is here. So this particular thing is the delta. So you have a bunch of errors. These are called errors, right? These are called loss, error. So this, you want to find a curve which minimizes this loss. So how do you know that you have a good formula for income and years of education? Is when your errors summed, all these errors summed together. You wouldn't just take one error, right? You take the sum of all these errors together, and when you have minimized that error. So here you would find some error. The goal is to find the curve, the blue curve, which minimizes this error. Now this whole thing is in one dimension. So you're talking about income with years of education. Now if you add another variable like years of education, seniority, and income, then you have this three-dimensional curve. And again, the same thing, instead of guessing a line, you're guessing a surface. And again, you have errors, this blue surface and this red dots. There is some difference here. You would again measure all the difference. And based on this difference, you'll try to find the surface which minimizes all of this, which keeps this thing to the least. So this is how the process of machine learning actually works, right? Any questions on this? And the way you do it is you keep on guessing one blue line after the other, and then see when you have the least error. All right, then moving on. So my experience in the AI space. So this is the machine learning work and AI, machine learning based AI is what I have been working on for the past many years now. There are some examples of the kind of work that we do in Freshworks. So in Fresh Service, for example, like I said, I think during the introduction, somebody said it's ITSM product. So we get tickets, our customers get tickets. So I mean, if in your organization, you would also have a help desk, right, to send tickets to. So this is a feature. This is something which our customers see as feature, where they get insights about the types of questions their users are asking. So the IT team of any company would get an insight that many of their users are asking password reset questions. How do we know password reset is the question? We receive multiple tickets. This is ticket 1, this is ticket 2, this is ticket 3. Ticket 1 is on VPN, ticket 2 is on password, ticket 3 is on password, and so on, right? From this body of ticket, we use machine learning to find out whether this is a password reset ticket, or this is a password creation ticket, or this is a password not working ticket, depending on what kind of things they have. And then so there's a lot of text written here, right? There's a lot of email here. We have a technique to find from that email, recognize that this is the main thing that is getting discussed in this ticket. So this ticket could be like the full page ticket, but we know in the end that this is the password reset is the only thing we're talking about. Similarly, this mobile Okta verification could be another ticket. Microsoft Teams could be another ticket. Slow system could be another group of tickets. So this is a system that uses an area called natural language processing. This is called NLP. Natural language processing is the way in which from an unstructured email, like a ticket, we are able to identify the main keywords or the main topics for these tickets, cluster them together, group them together into some meaningful way, and give this as a report back to the administrators. So this is one feature that my team works on, right? Any questions? Please add it to the question, the Q&A section. This is another feature that we work on. This is again based on natural language processing. So what you do is, this is a Slack interface where you have a service bot, and you can go and ask the service bot questions. Like you can ask, what are my insurance benefits? And the service bot will give you this information that your family eligibility is whatever, 3 times salary minimum, so whatever is the information, right? So this information is, in this case, we know the question, and using this question, we are able to understand a good answer to it. And the system in the backend, the AI in machine learning in the backend kind of figures this out. Now, this is a great advantage because a human being sitting here trying to answer all these questions would be a very expensive thing for the organization. In this case, some of the simpler things get answered directly here, and only sophisticated problems, complicated problems go to the agent. So there's an advantage of doing this. This is, again, as I said, the area is called NLP, natural language processing, a very interesting area of AI where we all spend a lot of time. This off late last 3-4 years, there's a lot of advances in this space. Similarly, let's skip this. This is basically raising a ticket. So if your problem doesn't get solved, you can also raise a ticket from here. Another project that I worked on, this is on the computer vision space. This is not in Freshworks, this is from my previous companies. This is on protein crystallization. So what you do here, these are again deep learning methods, deep neural networks, which we just saw. Medical companies, right, people who develop drugs and all, they do these experiments on finding crystals. So if you look at this image, right, there's a crystal which has formed here. There are crystals which are formed here. And they want to know how and when crystals are formed. This is, by the way, the image is through a microscope. So there's a high-powered microscope which actually shows you this image. You can't see them with naked eyes. But what we want to do is we want to see if crystals are present or not. Instead of a human being sitting on a microscope looking one image at a time, can we see if this can be done automatically? And in this case, we again used machine learning techniques of image processing to predict the protein crystallization. So there are different types of crystals which can form. And you have to basically, so this, if you look at this, right, this is one of them is looking like a pin. So that's called some pin crystal, then some amorphous crystal. And basically the crystal that we want is those cuboid shaped ones. Right? Those are the crystals that are required. So we use computer vision AI techniques to solve for these problems. And like I said, these systems are much better today than human beings. So they can detect crystals in a much accurate way than human beings. Plus, they are easier to sort of, they can work for more number of hours and so on than human beings can. So therefore, definitely an advantage for these kinds of systems. Next point that I want to address in this is these are all cool things, but how do you actually make it work, right? Oh, sorry, I missed that slide. So let's go back. Right. So how do you train? How do you get to this crystal thing, right? So what you do here is you take these images which are coming in from your microscope, right? You take these images and you get a human being to annotate it. So the process of machine learning starts with data. So here is one image of your crystal, right? This is an image, and here you have a small crystal which has formed, right? And there could be another image where a different kind of crystal has formed. So you take these images and ask teams who are experts, you train them, and you ask them to manually tag them. So they look at these images, and they say whether this is a crystal or not. And they do it for many crystals. So typical this image deep neural network crystal would need approximately 10,000 examples. So 10,000 such images will be looked at and manually annotated by expert human beings. Once we have these 10,000 images, these images will go into our deep neural network. This deep neural network will learn that function, right, which we talked about, function which predicts X, Y based on X, income based on the similar type of function will be learned. And once we have learned this function, we will use this function to predict a new image. So a new image comes in with some sort of thing which we don't know. We will push it to this function, and output will be one of these things. So this is how a machine learning system is developed. This is the same for text analytics also. For example, in Freshworks, what we do is we have teams who manually look at different queries from our customers and categorize them into types of queries, right? Like we have certain types internally that they categorize into types of queries. And then those categorized queries are what we use to build our models. So The model doesn't appear in sort of vacuum. You need human expertise to get started with that. But once you have these 10,000 examples, you will have this function. And after that, you don't need to do anything. This function will remain the same forever. And it will keep doing a good job, highly accurate job forever. The only time you need to change it if, let's say, you start getting a brand new type of crystal, right? Now, this brand new type of crystal is not present in this 10,000 data set. So that this 10,000 data set doesn't know about this new crystal which has come in. And at that time, this whole thing will fail. Then you have to collect more examples of this brand new crystal. Instead of having 100,000, you might add and make some 120,000 examples, retrain your deep neural network, get a new function, and then create the prediction. But till that point of time, your system will remain reasonably in a good shape. Okay, so this is some examples from various fields. I have taken you through a journey of multiple years, starting from early statistics, reliability kind of analysis, to data science techniques in retail space and so on, to experimentation using randomized control techniques. And finally, this area of artificial intelligence, where we are using techniques like computer vision, natural language processing, and machine learning based approaches to sort of solve for all of this. All right, thank you guys. That's all I had. I don't see any questions on the chat, so to you, Pragya.
Thank you, Saurabh, for such an insightful session. And I would like you to pick up one of your favorite questions, so that we can reward them with the Taylor Scholarship.
And where do I look at the chat, right, for the questions?
Yeah. So, audience, thank you for joining. And it was a really insightful session from your side, and keep learning. So once Saurabh decides, we'll award the person with the Taylor Scholarship.
I don't know. I don't see too many questions here, but I think this point is probably one of the important ones. That is, Lokesh is saying that previously watched movies and related content is basically what creates that recommendation system.
Okay.
For Netflix.
Congratulations, Lokesh. Our team will get back to you. And thank you, Saurabh, for your time and your efforts. And thank you, audience, for joining. Happy learning. Stay safe. Good night, everyone.
Good night.